Hello and welcome to the first lecture video for Chapter 13. Chapter 13 is on the topic of electric circuits, and this is from the textbook, The Physics of Everyday Phenomenon, a Conceptual Introduction to Physics. This is the 10th edition, and this is Griffith and Browsing. Okay, so this is our lecture here. We got the PowerPoints, and we will be going through these slides for the first two sections, all right? Although apparently I've gone to the last slide by accident. Well, there they all are. And there's obviously a way to take a shortcut all the way back to the beginning. Huh. Well, anyway, so here is the chapter, Chapter 13. Take a look right over there. We can see that we're talking about circuits, like the power grid. People talk about the grid, and we imagine the connection between power generation, so power plants, coal, nuclear, hydroelectric, solar. All right, we've got, of course, wind power. So all those types of power generation are then going to get connected into a network of transformers to change voltages as needed and then deliver that power throughout a complete circuit, okay? So every device that's going to be plugged in is going to be part of a loop. So it's not like the power plant just has a unidirectional line running out of it. It is part of the loop, as is every receiver of the electricity from the power plant, okay? So that's what we mean when we talk about building circuits. If we look here in the first section, we're going to have some concept questions about building very basic circuits, but they all involve loops, okay? So if you replace the power plant with a battery, then you can have a complete loop, but just like the power plant, like I was saying, there has to be an input and an output. It is a continual process because otherwise the mechanism of energy delivering is going to be the movement of electrons, and if it's not a continuous loop, they can't keep moving, okay? So we could compare this to hydroelectric, the flow of water, right? If the water isn't flowing, then you're not going to get any power out of those turbines that are being moved by the pressure of the water, right? Well, similarly here, you're not going to get any energy and through the light bulb. You're not going to be able to keep the light bulb glowing, a good manifestation of electrical power becoming heat mostly, but also visible light. So you can't keep that unless the electrons keep flowing, just like the water has to keep flowing. But in the case of the water, well, we know that, I suppose, if the lake dries up and you can't run the power plant anymore, why would the lake dry up? Because the water cycle stopped working, right? Because otherwise the water is a loop. It's going to flow into the oceans, it's going to come back up out of the oceans, into the clouds, very simply put, and then the clouds will rain down that water. That will continue a gravity-fed loop of water movement, okay? So in the case of an electrical circuit, you have to have a continual loop. It's not gravity fed, it's fed by electrostatic potential energy. The idea, the very concept of the Coulomb Force and the fact that any force can do work, therefore we have a potential energy created by the work done by the Coulomb Force, as the Coulomb Force having been discussed in the previous chapter, back in chapter 12. So that's the energy instead of gravity. It's that electrostatic energy, all right? And there can be another step before that. I mentioned it because if you look at the battery, it's chemical energy within the battery, and that energy then is going to turn into electrical potential energy, and then immediately be available to create a current. It's very easy to think of the current as like kinetic energy, because of course in the case of the water, zooming in a bit here, and that water cycle I mentioned that runs the hydroelectric dams, which is a generation point for electrical energy, bringing types of energy back around, really seeing it converted from one place to another. It's part of the grid, right? And there's obviously nuclear power plants, I mentioned them in passing, right? Then we got a whole nother force and a whole nother source of energy, but all together, all interchangeable to some extent, okay? Within limitations, as we know from the second law of thermodynamics, right? So, basically more orderly energy cannot be created for free from less orderly energy. That always applies. Okay, sometimes more relevant than others. In fact, when we talk about a lot of these electrical processes, they're very efficient in terms of kind of how much messy energy there is, how much disorder is created. There's some, right? You can't have electrons move perfectly unless we're talking about superconductors. But for the most part, there's always some resistance. There's always some lack of ideal. So as I was saying though, with the gravitational potential energy being given to the water, and then that water gaining kinetic energy, right? Because that's what's happening here. The water's falling. If we give it a nozzle, it can speed up and fall, and then achieve a pretty high speed. And what can happen then is it could hit something. In this case, it just lands into a tank, but it could hit something like a turbine and spin it, right? Turning that energy, the kinetic energy of the falling water, which came from the gravitational potential energy of the water. Well, it could then spin a turbine. That turbine then could be part of a electromagnetic generator, which we'll talk about in chapter 14, which means it's just the way we create power. Basically, every power plant, whether it's coal, whether it's hydroelectric, whether it's wind power, even to some extent, some large solar power stations work on this idea as well. They basically all involve the movement of water, either through gravity or through some sort of boiling of water, because then that movement of water, the boiling in the case of a coal power plant or a nuclear power plant, very, very hot steam, rises up and spins a turbine. In the case of wind power, the wind itself directly spins the turbine, so that's kind of cool, right? The falling water and the hydroelectric spins the turbine. I said with solar power plants, sometimes they actually aren't your hydroelectric cells, which is actually a photoelectric effect, kicking electrons out of a metal, essentially, or out of a semiconductor or something. So kind of a different mechanism, same physics, but sometimes a giant solar power plant is not a bunch of the types of solar panels you would install on a residential roof, but instead large mirrors that are all focused on a tower that is a kind of traditional turbine system that has all that light energy coming focused on one spot, boiling water at very high temperature within particularly efficient systems of spinning turbines and pressurized steam and generating a huge amount of electricity by spinning something. And it does come down to, as we'll discuss in the next chapter, right, chapter 14, is that it does always come down to this idea that if you spin a current, okay, or rather in this case, if you spin a wire, right, so like a circuit, because it's got to be all the way around, so not an open wire, but if you spin a closed wire within a magnetic field, it's like there's a battery attached. Okay, now I'm totally getting ahead because this is in chapter 14, but it's literally like you get a virtual battery. So you would just have the wire, you could put a resistor in there, right? Like a battery to see the effect, right? And you spin this thing within a magnetic field. The magnetic field has to be perpendicular to the spin. So if this thing was literally spinning, right, imagine the switch kind of going in this direction around counterclockwise, okay? Because counterclockwise is positive in physics and mathematics, so we kind of tend to say counterclockwise instead of clockwise. But imagine that, right? Spinning around, okay, so the whole thing's spinning around. In the plane of the page, if there's a magnetic field in and out of the page, that's where you get electricity. That's how you get the virtual battery, a term I just kind of made up, but it's relevant to this figure because you get this idea, you get a voltage, okay? You can generate a voltage, and that's what all power plants do, all right? Now here we're generating a voltage through a equally not well explained in this chapter mechanism that we kind of write off as a different field of the physical sciences, the chemical energy, the chemistry of a battery, right? That somehow contains energy and is able to release it as electric potential energy. Now the electric potential energy we have talked about specifically because again that's literally just the work done by the Coulomb force or the external work done against the Coulomb force to move two charges apart. Right, holding them apart, essentially then letting them come together, releasing that electrical potential energy, which then can do something else. It can become the electrical equivalent of that kinetic energy that's capable itself of spinning a turbine, as I went off on a tangent on. Essentially, just that kinetic energy of the water is capable of doing work, generating power, okay? And we'll definitely understand these circuits through the context of them generating power. It's a great way to think about it. So then what's the equivalent, right? Is there just straight up kinetic energy going on in the wire? Well, no. Because it turns out it's the electrons that carry the energy. It's the electrons that are current. So when we talk about one of the biggest key terms of this chapter, one of the big new things is it's not electrostatics anymore. It's electrical circuits, which is to say electrodynamics, just the movement of charge, and the term for that is current. That's the actual physical variable. Well, the variable is I, but the name of it is current. So that's a big thing we're going to be talking about, but it's not kinetic energy. That's why I keep asking, because I keep saying, oh, is it just kinetic energy? No, because we're not actually going to talk about the 1/2 mv squared of the electrons. That would be their individual kinetic energy. There's a big reason for that. One is that because there's a lot of random motion of them, and there's something called the electron drift speed, which we will not cover. You are not responsible for, within the context of this textbook. But it's interesting, and it's more of the random motion of the electrons, and it's tied in with the resistance of wires and this idea of very low resistance wires, right? Then you have much more uniform motion. But even then, the electrons are never moving at the speed of the electric field. Because remember, one of the big abstractions, but also very useful ways to think about electricity that we saw at the very tail end of chapter 12 was both the concept of the electric field and the concept of voltage. Okay? Closely related, all right? Voltage is like potential energy. Electric field is a force field. It tells you, where things will go if they're released, okay? And all the little kind of the lines and the field lines, as they're called, they point in the direction that a positive charge would be accelerated in. Cool, right? Directly related to the force, Newton's second law. Neat idea. So I bring all this up because, within, you have that field, you have that field, the work that was done against the field, and that gain of energy. But that energy, it's going to move. The field is going to move at the speed of light, and the electrons don't move anywhere close to the speed of light, even if their motion is not as random as it would be in just a typical copper wire or silver wire or something. Okay, so slow moving electrons, really slow moving, actually just like centimeters per second, but field, so kind of like influence, just like gravity, that moves at the speed of light. Okay, and as far as we know, by the way, gravity moves at the speed of light, also can be transferred as a wave, which was recently proven in very modern physics. This idea of gravitational waves, which are like EM waves, but not really, but cool stuff, right? But anyway, so the electric field is also the signal of light itself, the influence of it, the signature of it, right? Signal/signature. So moving at the speed of light, okay? So as that field moves through the wire, that's what then has the potential to do work. So that's the much more kind of interesting and not as easily graspable concept as kinetic energy, okay? It's the creation of the field, and then the field can influence anything in its path, okay? And what is capable of influencing are charged particles. Free electrons in a metal are a great candidate because they're free. They're ready to get moved along by whatever is the general direction of force. Okay, they'll bump into each other and bump into the fixed atomic nuclei within the metal and so on. But they're all going to it's like they all got tipped to the side and they all want to move in that direction. If we're going to the analogy of kind of like a fluid, in this case a fluid of electrons, tiny little balls, right? Trillions upon trillions of them, kind of rolling in one direction, the downhill direction, which is the direction of the electric field. Okay, although be careful, because the electric field was built on the concept, on the convention, which turned out to be wrong, that positive charges are the charges that are free to move. Okay, but it's not. Metals are the most common conductor, and when metals conduct, they conduct free electrons. That means that when you look at the direction of the field and the direction of current, this term that we're getting into in this chapter, that it all points the other way, which is to say it points the way that electrons aren't moving. It's 180 degrees the other way. Electrons move that way, current points that way. Weird, right? Again, just historical baggage, it's the convention. So, most of the time maybe you only care about current. That's great, you just point in the direction of current. But remember, if you are asked about electrons, they are technically going the other way, okay? In any wire, metal wire that is. Okay, so anyway, so you have the influence of the electric field, and whether it's causing electrons to go one way or these imaginary free to move positive charges / current going the other way, whatever's happening, that's the influence of the electric field. And that's the energy, because now all that's there, that's capable of moving, will do so, okay? And then whatever is the parameter of the channel, so to speak, right? This idea that then the wire is going to facilitate the movement of those electrons, whereas the air around aren't, because so you don't really notice the effect of the field. The field's everywhere. It's not just in the wire. The wire is just a place where it can easily manifest itself. So now you got the electrons moving in the direction of the field, right, or the other way, but still parallel to it in a vector sense. So well, then, right, can the energy do something? Can it show up, right? Can we really see that potential energy become something else? Yes. As soon as the bumping starts mattering, as soon as all the interaction of the electrons with their surroundings really do something. And that's what resistors are great for. That's why we show the light bulb, because the light bulb is what is called a resistor. It turns that current, which came from electrical potential energy, into heat through random motion, right? Bunch of molecular shaking. Then that shows up on the macroscopic world as light and heat, okay? So cool idea, and of course it can do other things, right? And it can create a motor, for example. I talked about generators. Motors are kind of like generators run backwards, cool idea. But whatever it is that you're using the electricity for, it had to become current first, which we can understand through the electric field. To see a tie-in with the previous chapter, all right? Although the concept of the electric field will just naturally come up as we proceed. So a flashlight, an electric toaster, and a car's starting motor all involve electric circuits and electric currents, finished loops, okay? If you break the circuit, right, that means you broke the device, if it's an electrical device. How does electric current resemble the flow of water in a pipe? I think I've started to answer that, right? It's a great analogy. Now, if you have these, just three things, a little wire, okay? It's got two ends of it where we've actually exposed the metal inside, right? Okay, and we've got a battery, okay? It's charged, we'll assume, and there's a single little light bulb, all right, like a flashlight bulb. Now, if you don't know, I'll tell you, right? These things have two ends, so they're kind of like, they're really like any like input-output sort of a device, right? Because you think about like a prong that you plug into the wall, right? It has an input and output. Sometimes it's also got that third designated ground. But or some sorts of really simple electrical devices like little diodes or things, they'll clearly have one wire on each end, right? Really showing, I guess a battery is a great example of that, right? Really showing that everything that you take and put into a circuit, it all has to have an input and output because it's got to go into the circuit. So on the bulb, I think the diagram shows a good job of it. There's two essentially wires that just don't look like it, right? So everything on the outside is, we could call that the input, and then it's insulated. You can kind of see the dark region here. So there's basically a cylinder, like a hollow cylinder of insulation that runs all the way up. So that means that there's metal, continuous metal, that then would be connected to one part of the actual resistor, all right, kind of going into the bulb, and we have a cross-section of it later on. And then it would come back out the other way, not touching that metal again, and then come out the bottom, right? So there's a path that comes out of the little metal bottom part shown here, right, that is insulated and able to run through the exterior metal part. So it's actually an actual continuous path, right? Because otherwise it would just short itself out, would be kind of the effect, okay? Which is, of course, a sort of a jargon term, but just mean that it'd be like just a wire, right? It wouldn't go through the high resistance part that has to glow hot. Because the reason, by the way, that the bulb glows hot and the wire doesn't, ideally, right? You don't want your wires to melt. That can happen sometimes. But the reason is because the bulb is really high resistance. It's tiny, which contributes to high resistance, and it's made out of certain materials that glow at certain desirable temperatures, which then correspond to certain wavelengths of light, according to Wien's law. So all that, what I mean then is that it's a high resistance on purpose device, which makes it, right, glow. Okay, so can you actually build a circuit though with just these three things? What do you think, right? There's no switch, right? But could you do it? What do you think? Okay, hopefully you got an answer. So we got three options down below. I won't give you the answer right now, but would any of these three, or maybe more than one, create a actual circuit? And you would know that you've done it, that you were successful in creating a closed or complete path, in other words, a circuit, if the bulb lit up, okay? Because that means you got that full process, that continuous flow, all right? Energy is able to get converted, in this case to heat energy, and a little bit of visible light, Right? I say it's a little bit of visible light because that's the thing about light bulbs, traditional ones, is they create all these other wavelengths outside of the visible spectrum. So they're more about creating heat, right? Which sometimes is not what you want from them. So they're all kind of inefficient, very inefficient in a sense of just creating visible light. An LED is not. All right? That path is called a circuit, a complete circuit. If any of these are, that is, right? But we've seen some already. Okay? So, turns out there was one, right? C. C was the only one. Okay? Did you catch Y? Did you see on B what's wrong? It's darn close, right? But we skipped the bulb. Yeah, sure, it's touching there. But the path, okay, the path of the current, we'll talk about that idea a lot, right? The current follows the path, all right? Well, the circuit now has skipped over the bulb. Yeah, it's like a little like offshoot. And you know, there would be no way, however, to go in and back out, right? There's only a way in, there's no way back out. It's a dead end, see? All right, so in this circuit, the battery is the energy source, right? Chemical energy, we assume. All right, to separate the positive and negative charges, that's what the chemical energy did. This leads to a voltage difference, okay? It's really easy to go from energy to voltage because literally you just take joules and you divide by coulombs, right? Remember coulombs are the fundamental unit of charge, this new property of matter, right? Well, property of particles, okay? And what's cool though is that that's all voltage is. Joules over coulombs. We say it's energy normalized by charge, okay? Volts. All right, so voltage difference, right? Read potential energy. With an excess of potential charges at one end of the battery and an excess of negative charges at the other. Great, right? You're holding them apart, they want to come together. See? You can release them. Release that energy. These charges will tend to flow from one terminal to the other, all right? If we provide an external conducting path, the circuit. All right, so let's define something I've hinted at a ton in my long, rambling introduction, but I hope an interesting one. Right? I want you to get some of the interest of this concept. So fascinating. It's many connections. There are tangents aplenty you can discuss with electricity, right? Let alone electricity and magnetism, which obviously I'm chomping at the bit to start discussing. So a flow of electric charge, by definition, is called an electric current. We'll usually just call it a current. All right, it is defined as Q over T. Okay, so it's not a velocity, it's not meters per second at all, all right? Instead, it's Q per second. It's charge per second, coulombs per second, charge per time, all right? There's the unit, by the way, represented as uppercase A, right? That's the unit. The variable is usually I, but the unit's uppercase A. Got it? All right? And it's in terms of other units, it's the coulomb per second. So it's a pretty fundamental unit because the coulomb is the new fundamental one, depending on who you ask. Technically, it's the ampere. But we can see that graciously, whether we're agreeing that the ampere is the fundamental unit, which is the name for the amp, by the way, I'll fully call it ampere, that unit of current is it, or maybe the unit of charge, which makes more sense to me since it's the property of the particles, right? Like electrons and protons. Right? So that's the new fundamental player, right? The thing that we added to our short list of base units. Kilograms, seconds, meters, Kelvin, Coulomb, okay? Or ampere. But they're so closely related. Ampere and Coulomb, right? Because the Coulomb is just the ampere second. The ampere, right, is just the Coulomb per second. Right? So again, not velocity, right? It's more like a mass flow rate, which we briefly talked about when we talked about fluids, because it's how much of this thing, charge, is passing through some cross-section, okay, per unit time. That's what it is, okay? So it would be like kilograms per second, right? We saw that, mass flow rate, all right? But here it's charge flow rate. So, for example, if 3 coulombs of charge flow through a wire in 2 seconds, then the electric current is 3 coulombs over 2 seconds, or 1.5 amps, 1.5 amps, all right? And there's big things, like we definitely assume, it's uniform, right? We don't have like, varying current, backing up in some places, changing. The only time current ever changes in a introductory model to circuits is at a junction, right? And then it follows a really, really straightforward rule, which is totally intuitive, which is that it's summed up, right? So you can't have like, 1 amp of current coming into a, like a Y junction, okay, fork in the road. You can't have 1 amp coming in and then have like 6 amps coming out, because where do the extra amps come from, right? And you can't just lose amps either. And be like, well, couldn't you just convert them that, no, really, no, because they're based on the actual charge. And the charge isn't just going to disappear, okay? It's not just going to cease to exist, all right? So conservation of charge is really the name for this idea, but effectively it's conservation of current, right? What flows in must flow out, right? If you know what's flowing out, then you can figure out what flowed in, as long as you know your channels, right? In the simple case being a fork in the road, right? Or two paths coming together. So, by the way, I said this before, this is that heads up, weird rule that current flows or points or flows, right, in the direction of positive charge, which is shown here in figure A. And then remember, electrons are what actually move in metals, which is what we actually care about. And the electrons, most of the time, are then going to move exactly the opposite way, okay, anti-parallel, right? All right, and that's what it says at the bullet point. Okay, so the direction of current is defined as the direction of those positive charges, just historically. All right, it's too late to change it if that's, if you accept that explanation for it. All right, so the charge carriers and metal wires are the negative ones, they flow the other way, right? But we usually just won't talk about them because we have a set of equations, whether those are ones like Ohm's law that we see in this chapter or whether those ones like Faraday's law that we see in the next chapter, that are all based on current. So we stick to working with current. We only ever have to think about electrons as like a last step, and they just go the other way. Big deal, right? The important thing is to be consistent of always working with current, at the beginning at least. All right, so this is that cross section that I mentioned for the light bulb, which is really kind of clearly shows that there's this insulator, so that the path through the middle is completely separate. Here shown is just a thin wire, right? Because functionally that's what it is. That then goes up through the filament, which is an even thinner wire, designed to glow hot with its very high resistance. And then, then on the path probably in, right, was this way, right? So this was the way in, so you can just see it's one path in, one path out. You put it into a circuit, it continues the circuit, all right? So a property of wires, which is usually an undesirable property of wires and not terribly large, is resistance. And it's also a property, as I said, of filaments, and you want it to be large, okay? If you want the light bulb to glow. If the flashlight bulb, a very thin wire filament, restricts the current because of its very small cross-sectional area, because I said, turns out one way to do that, to have high resistance, is just to be a small wire, which actually makes a lot of sense because that works with the fluid analogy, doesn't it? Because if you confine a fluid to a super narrow channel, what happens, right? Well, you've forced it to speed up significantly, okay? Well, that's great, right, for our laminar, there's a key word for it from a previous chapter, right? Our laminar flow situation where we could, use continuity and everything was perfect. But remember what fluids could do? They could become turbulent. Well, resistance is all about that type of energy, that high entropy, very disordered type of energy, right, which is called high entropy, which is those electrons bumping into each other and bumping into the sides, more likely to bump into the sides when the wire is really small, okay? Well, that is what becomes the heat energy, okay? So being narrow now isn't about speeding up the current, all right? There would be actually some marginal increase in the kind of the average velocity of electrons in a kind of classical fluid sense. But what's way more important is the fact that you're messing with the current. You don't lose it because the current, it remains completely the same all the way around. The current cannot change, remember, right? Because it's still the same number of charge carriers, but it's capable of doing work. The voltage can change, all right? Because the current in a loop goes all the way back around, right? It represents that continuous flow. And it's that mechanism of being able to change forms of energy. That's why I keep coming back to it. At least that's why I started with it. But one thing I think I've explained, one thing I don't think I have explained, okay? I think I have explained it, is that current is understood, the way it does work, through the voltage drops across parts of the circuit that the current flows through. So if I was to look at this circuit over here, and I look at the light bulb, the resistor, okay? And this idea that there's gonna be a change in energy, it's gonna create heat from electricity. Well, there would be a voltage change here, a large voltage change across the resistor, okay? A large voltage change across the light bulb, because the light bulb is a resistor, Okay, so that's the idea, is we lose voltage, which is to say we lose energy, right? But the current doesn't change because it's still got to be the same number of charge, right? So there's just, it's just that it's dropped all the way down, right? It's like it was a river, it was the same river, right? And it came off the side of a big cliff, created a loud waterfall, right? Well, noise is a lot like heat, same sort of disordered energy. And so that loud waterfall, all the mist, takes energy to make that mist rise up, right? Well, that is like the glowing filament. That's the energy of the stream, okay, then becoming something else. The actual kilograms per second, the mass flow rate in the case of the river, didn't change, and neither does the current, because the current is the charge flow rate, and we didn't lose any charge. The charge just went off the edge of that cliff, turning the electrical potential energy into heat. So it's kind of interesting, right? So we need the current in a sense, and the current we'll see is directly related to the voltage, but sometimes thinking about voltage is the better way of understanding a subject, and especially these analogies, and sometimes thinking about current is the better way. So it's very kind of situational and just kind of how you want to come at these subjects. Make the most sense of them. And I really do think the analogies are so valuable for making sense of circuits and electricity, okay? And of course, magnetism. So 2 arrangements of a battery, bulb, and wire are shown below. Which of the 2 arrangements will light the bulb? Both, neither, or just A or B? Okay, so this is like the one we started with. What do you think? All right, so you probably were able to rule out B because it's more or less identical to the one that we already ruled out before, so if you're paying attention. But then does this one work, right? Does A work? Absolutely. So it's just kind of the reverse of the other one that we saw that worked with this simple case, right? And there's other ways of doing this, by the way. You can use a rubber band, right? But if you really want to be simple, you can kind of hold it together this way somehow, right? Balance it. And here, though, we just put the bulb in, like I said, the other way. Right, so instead of having what we might call the output touching the terminal of the battery, we have the external part that's insulated from that little central part. Right? Well, we have that as the part touching the battery, and it doesn't matter. Right? The bulb's going to work the same, regardless of how it's lined up with the current. They're completely unidirectional. Right? They work the same both ways. Right? So bidirectional then maybe. Maybe omnidirectional. Just that they work the same both ways. I'm just trying to think what the term would be. All right, so more on that official definition of current. We know the units now. Coulombs per second, the ampere. All right, so water flowing in a pipe is similar to the electric current flowing in a circuit. All right, have you heard this before? The battery is like the pump. Okay, cool. It's funny here because the pump is probably like literally electrical energy, right? So it takes the analogy full circle. I guess you could have like a mechanical pump though, driven by a biological source of energy or nuclear energy. The electric charge is like the water, okay, right? So I kept saying, it's really comparable. Mass flow rate, kilograms per second, is like current, charge per second. The connecting wires are like the thick pipe. Absolutely, okay? Now, why thick pipe? That's interesting, right? Put that word in there. That's to imply low resistance, because good wires are relatively thick, which doesn't have to be like macroscopically thick. They just have to be, maybe approaching a millimeter or something, right? Because on the scale of electrons, that's really big. And so then the idea is that that's going to be your big thick pipe, which offers very low resistance. It's very easy to move the electrons through without causing them to do all that bumping. That is the change in energy. That is the catalyst, the mechanism for changing one form of energy into another. Okay. And the switch is like the valve, which makes sense. You can turn it on and off, right? You can open up the circuit, in which case nothing happens, okay? You're not going to be converting electrical potential energy into heat if that switch is open, because there's no way to keep the electrons moving, right? And they're the carrier of the signal, the electrons are. So in a water flow system, a high pressure difference will produce a large rate of water flow or current. The high pressure can be produced by raising the storage tank, right? This pressure is related to the gravitational potential energy, see? That's why I said that's what drives the system, the potential to do work, okay? Likewise, a large difference in potential energy between the charges, electrical potential energy, okay? That is going to create a high voltage, because it's so easy to go from energy to voltage, just divide by charge. So if I wanted to know how much volts my battery has, that's literally the joules that are in it divided by how many, electrons essentially there are in it, and what's the total charge of all those electrons. That's kind of cool, right? So, that's when you talk about a 9-volt battery. If you know one of those other two numbers, like, the number of charge carriers available in the 9 volts, well, then you're going to be right at a place where you then be able to actually calculate the joules. People don't talk about that a lot, right? How much energy is in this battery? Well, there's ways to find out, but you need one more bit of information to know how many available electrons there are, which varies between batteries. All right, oh, sorry about that. All right. Oh no, I showed you the answer. Sorry. All right, carrying on. So in the circuit shown, the wires are connected to either side of the wooden block as well as to the light bulb. Will the light bulb light in this arrangement? But right? Make sure you got an answer on this one. Okay? No, right? Because the bulb, you might know because I just showed you, it's what is called an insulator. We defined that pretty thoroughly in the last chapter. Definitely will not complete the circuit. It's not enough of those free moving electrons to keep that chain reaction, keep the signal alive, right? So in the circuit shown, could we increase the brightness of the bulb by connecting a wire between points A and B? Would that help things out? Symbols here, right? Because this is our kind of our new language of learning how to read these circuit diagrams. This right here is the symbol for a battery. The curly E stands for, in terms of kind of like historical reference, EMF, which was what early voltage was called, and literally stood for electromotive force. But that's a terrible name because you shouldn't call something force by name when it is not a force in units at all, right? It's not like the battery holds a force, which is also a huge misconception in physics, and you wouldn't want to encourage that, would you? But we still refer to EMF, although we've apparently dropped the meaning of the acronym, and it's just literally the letters EMF, and we use that curly E as a further shortened version, which just stands for voltage source. Okay? Now, it does have its advantages because V is an overused letter, so referring to the voltage as V can be a bit of a kind of a problem if you need to talk about the volume of something. So, get used to seeing that curly E representing the voltage of a battery. Now, would this actually increase the brightness? No, not at all, right? It would essentially short out the circuit because the current will flow in the lowest resistance path. And water will do this as well, right? I mean, it's not going to flow uphill. And if you give it an option to flow, on a steeper path, then the water will take it. In the context of sort of the topography of a landscape, that those channels that water flows down, that's the watershed and the shape of it. In a calculus language context, we call that the gradient. It's the direction of downhill that then can be abstracted to things that aren't literal landscapes, like a voltage landscape. So what's known as a potential surface, because there would be a bunch of equal potential lines, which are completely analogous to elevation lines or altitude lines. And elevation, I guess, altitude is when you go up in the air, so elevation lines. And so then that's your idea, is you've got these stacked up lines, they represent uphill and downhill, and what's going to happen is the current will flow, well, straight downhill the steepest way it can, right? It won't just flow across the flat land if there's a big ravine to the side, right? Water flows down through the ravine. So will current, all right, with its comparable charge per time to mass per time flow. Well, there you go. It's just going to go right through that wire because it's a much easier path. It's a steeper downhill path. Nothing's going to flow through the challenging narrow path through the rapids, that was rapids of the resistor, and it's just left dry or without any current. All right. So which of the two circuits shown will cause the light bulb to light? All right. So this is very much like the picture one. We're just using official circuit diagrams now. But the picture one, I mean the ones that showed the cartoon of the battery and the wire and so on, right? Right? B, right? So B definitely works. We got a complete loop. We have an open switch, but it's off to the side, so it doesn't matter, right? So it's a dead-end channel to the side, which is doubly important because if it was closed, then we'd run into a situation where we'd have, actually, would that matter in this case? Because we have those two side paths. But neither of them is parallel to the resistor, so it wouldn't matter. So even if it was closed, actually, it would make no difference, because if the wires are approximately zero resistance, then both these paths are equally likely. And so it won't affect anything, and they're just going to reconverge and then still flow through the resistor, which is to say the light bulb would still light. Yeah, so closed or open, B would light the light bulb. On the other hand, this one doesn't at all because we're missing one terminal of the battery. That's always a big no-no. Okay, so suppose we use an uncoated metal clip to hold the wires in place. All right, this is funny too, because when I kept seeing the pictures early on, I kept thinking about something. Because if you go back here, see these ones? There's that brown, stripe around the battery. What is that, right? It's a rubber band. That works pretty well because the rubber band is rubber. Okay, but over here, right? We're told that this one works. Well, the problem is that I've done this, and unless your skin is like really dry or something, then your hand's gonna conduct, and what's gonna happen is there's gonna be a path that's gonna go right into your body, and it's going to potentially be the easier path compared to the very high resistance of the filament, and the filament won't light up because you're giving the current an opportunity to flow through you, right, to somewhere, right, kind of discharging somewhere, right, maybe on some vast part of your body compared to the tiny resistor filament. So that's what I'm saying, right? That's unlikely to actually work. The rubber band is much closer to reality, and this clamp brings us also back to reality because they make sure to mention, authors of the book, that it's uncoated, which means it's just a big piece of metal, and metal conducts, so no. The metal clamp will definitely provide a path, and the bulb will not light up. It'll be an easier path. Now, it's probably not going to be a great path. It's not like the metal clamp will heat up because it's like one giant resistor, right? Especially not with the relatively low voltage of the battery. But still, it is the difficult to measure or see its influence, but still it is the path that the electrons will be taking, and they will not be going to the filament, and it will not light up. All right, so this takes us now, having defined current, to the last bit of this lecture video, because I'm going to stop before section 3. So like I said, this video I'm going to cover sections 1 and 2. Section 3 talks about parallel and series circuits, which is cool. It's kind of like that next step of understanding circuits. It's because it gets into the junctions, and it touches on one thing I've totally already mentioned, which is conservation of charge, but formalizes it. And then it comes up with, hey, conservation of energy. Nice, right? Conservation of energy is always a good thing to fall back on. We do it like in every discipline of physics, it seems like, which is great because it ties everything together, and it's just a neat story to tell, right? That we have this tool collectively as humanity of solving problems. Track the energy, okay? But before we get there, the last very introductory idea is Ohm's law. Ohm's law is considered one of the most fundamental laws of electricity. Now, that's interesting because really Coulomb's law, we saw, is the real building block, right? It's the fundamental force. It's the one it's comparable to universal gravity. It's the fundamental physics. But it doesn't really show up, actually, because you don't usually individually calculate the force between two charges, right? So it's more of a great idea for the physicist, great idea for the physics classroom, but gets less, kind of everyday application. Whereas Ohm's law matters because if you got a circuit, Ohm's law is going to be relevant. Okay, so I think that's why it's really such a springboard for understanding electricity, and it is in its own right a very straightforward fundamental law because it's what's called a proportionality law, right? So it's kind of like the ideal gas law, which ended up being joules on both sides. So basically an energy conservation law, but also this idea that we had a ratio of changes. It also honestly is very similar to, because it's a linear concept. It's very similar to Hooke's law, which might be a stretch of the imagination, and I may be thinking more, well, mathematically it is, but it also it is in concept, because you got two things in the case of Hooke's law, force and displacement, that are directly related to each other. So if you increase the displacement of the spring, the force goes up, right? The force pulls back more and more the greater it's stretched, okay? Or compressed. That's great, right? And it turns out that you got that relationship, which makes sense, and it turns out that they're linear, which means directly proportional, so then the equation just becomes y equals mx in a equation of a line sense, Or in the Hooke's law, F equals kx, okay? K was a spring constant, F was force, x was just x, displacement. So we have our own y equals mx equation, but it's V equals IR. That's it, V equals IR. 3 letters, directly related to each other, all right? What are they related by, okay? Well, they're related, as we can see here, by this concept of current, all right? And voltage, which we've already seen, and something new, right? We just saw current, but now we have an even new player, not a hard one though, resistance, okay? So we see that resistance is the actual ratio. It is the ratio of voltage to the current. So if I was to solve for resistance, do some cross multiplication in your head, right? R over here, R over there, divide by I, right? Resistance would just be V over I, okay? So it's volts per current. The higher the resistance, the more volts per current. The lower the resistance, the less volts per current. Ah, right? Because the rapids, the big waterfall, that's high volts per current. The current never changed, right? Because I said you had to conserve the charge, but you had a big change in voltage. And the fact that it's change, I wasn't just saying it because I wanted to say a simple word, not say delta V every time. Well, but that matters, right? Because it is always the change. The resistor creates a voltage change. In fact, it creates a voltage drop. There's a decrease in voltage, which is to say electrical potential energy is being released, okay? And the amount that's being released is dependent on how big the value of resistance is. So the resistance is a sort of like material quantity. It refers to the actual resistor itself and how it was made and what it's made out of, okay? The actual property of the materials is called resistivity, and you can look it up for different materials. And then the resistance comes from kind of the geometry of how the resistor was made. Now, resistance, being a brand new quantity, has its units. Now, we can see that its units, if we solve for it, are V over I. So that means it's volts per, amp. And volts are joules per coulomb. And then the amp is coulomb per second. Okay? So that's nice. It can show you directly what it is, right? Okay? Oh man, I should probably come back to that, write it down for you. Because if you think about it, right, what would be resistance, okay, if it's, I'll show you over here, right, because we know it's volts per amps, because again, if you solve for it using this equation and rearranging it, you would get delta V over I equals R, right, or R equals delta V over I, okay, so volts are the units of volts, that's a weird one, right, and then down below, okay, now that I is down below, the units of current are amps, so that means the units of R, this new thing, resistance, are volts per amp. What I was saying is that the volt is, by definition, the joule per coulomb, and then down here, right, the amp is the coulomb per second. So it should simplify nicely. Try it out, all right? But this unit has its name as well. So this is a derived unit with a name, okay? All right, so it's interesting here because we see that the units of resistance are named the ohm, represented by uppercase omega, and they're equal to the volt per amp. What's funny about this is this is not showing the ohm, which is to say the unit of resistance, in base units. Not completely, right? Not at all, right? This is not base units. This is a derived unit, the ohm, in terms of other derived units, the volt per amp. I bring that up because be careful with that, because if you get completely lost on units at this point in this next couple chapters on electricity and magnetism, it's going to be a lot harder to make sense of it. So bring things back to the base units when you want an opportunity to further understand the subject. So the resistance of a wire is proportional to the length, all right, so as I said, the geometry matters, inversely proportional to the cross-sectional area, wider wire, lower resistance, all right, and it's also inversely proportional to the conductivity of the material, which has its own name, the resistivity. There's inverses of each other, right? And actually, it's highly temperature dependent as well, all right? So consider the two signs shown. Which one would give you greater concern? Question is kind of like, do you kind of get a sense of the units, right? Have you seen them before? Yeah, so definitely higher voltage between these two would matter more. And if you're thinking to yourself, well, isn't there an expression that says it's not the volts that kill, it's the current, or it's the amps, right? But neither of these were amps, notice, right? So the focus of this sort of, interesting / goofy question was to say, 100,000 ohms doesn't really mean anything, right? The human body has hundreds of thousands of ohms of resistance. It's a pretty high resistance system, right? It can conduct a little bit because of like salt and whatnot in our system. but it's not great at it, you know. And if you think of the resistivity of air, and if you're going to ionize air, like have a big spark or lightning or something, it has a certain kind of average resistance per centimeter, and it's really high. It's going to be millions of ohms, you know. So that's interesting, right? So there are a lot of high resistances out there. There's also things that are really low resistance. You know, wires can just be a fraction of an ohm per meter. You know, they're very low resistance silver wires or something. So, okay, that's the meaning of resistance. It's more of an application of kind of like building something, not really a health concern, right? But high volts can be. But high volts also can be totally harmless. If you build up static electricity on the surface of a balloon by rubbing it on the carpet, and it has enough static electricity to hold your hair up a little bit, that has tens of thousands of volts, 50, 60,000 volts. But it's not going to cause any harm because there are fairly few charge carriers, right? Still trillions of them, but not like the almost unlimited source that would come out of an outlet. And so once you discharge it, that's it. So the actual power involves both how much charge there is, or how much current you can deliver, which is the rate of charge, of course, and the voltage. So really, it's the power that matters. It's not the volts or the amps, and it's certainly not the ohms. And we'll actually talk about how to express power with these new variables later on, but not in this video. All right, so Ohm's law is the name for this relationship between voltage, current, and resistance. All right. If we know the resistance of a given portion of a circuit and the applied voltage, right, such as the 1.5 volts from a battery, we can calculate the current through that portion of the circuit. By the way, A's, or double A's, triple A's, C's, and D's are all 1.5 volts. The only thing that changes is their amp hours, essentially how much charge they hold. Right, so capacity, but voltage doesn't vary between them. So for example, consider a 1.5 volt battery connected to a light bulb with a resistance of 20 ohms. Right? If the resistance of the battery itself is negligible, which is a reasonable assumption, all right, then the current can be found by applying Ohm's law. All right. You know what's also that's negligible, which is kind of funny, isn't mentioned? It's not just the battery, it's also the wire. So we're saying that the wire and the battery are both negligible resistance. All right, so the only resistance that of any substantial amount, maybe many orders of magnitude more, is the 20 ohms of the bulb. By the way, when I work with the little tiny kind of bulbs that you use in a classroom laboratory, those tend to be around 3 ohms for the resistance. So this is a little. This being a higher value will usually mean it's brighter, right? So this is a potentially brighter bulb, depending on how it's used. And we can solve for how much current passes through this particular 20 ohm bulb, okay, by solving for I, right? When we solve for I, it's volts over ohms. It's, so it's the value of voltage coming from the battery divided by the resistance of the resistor. And we get 0.075 amps, or a current of 75 milliamps. So a really typical way of expressing current, because it often ends up being in the milliamp range from the 1s to 10s, right? So sometimes the battery does matter, which is kind of why it was hinted at. So we ignore the resistance of the battery, okay, as well as the very small resistance of the connecting wires, which of those two negligible resistances, battery plus wires, the battery does generally matter more. If the battery is fresh, its internal resistance is in fact small, but as it gets used, its internal resistance becomes larger and larger, right? So the voltage of a battery, 1.5 volts, right, is called its electromotive force. That's why I use that curly E. And the increase in potential energy per unit charge provided by the chemical reactions in the battery. Okay, so check that out. It is the increase, so how much it has in it, in potential energy per unit charge. What is that? What is potential energy per unit charge? That's literally volts. That's all they're saying is it's just the volts, okay, of the battery, which of course is provided by the chemical reactions. It's a very long way of saying what we already know. Batteries have voltage, which for some reason can be called electromotive force, or curly E. Okay, so then when we have the loop equation, if we just want to think about what's going on inside the battery, its internal resistance, we can say that it's the voltage drop across it would be its internal resistance, R, and then the current that is shared by it and the bulb. So you can work that out as well. Okay, so if the internal resistance of the battery is 5 ohms, so 1/4 that of the bulb, so definitely not negligible, then the total resistance of the circuit, because they're all in the same path, is the sum. Okay? All right. Now, I could go off and justify this a bit more. I probably will more when we talk about parallel and series circuits. But for now, take it as believable that, yeah, just having the two resistances, the internal resistance of the battery and the resistance of the filament of the bulb, in one single path like this means that effectively you just sum them up. Okay? So then the total resistance of the circuit is 25 ohms. Therefore, the current through the circuit is going to be the 1.5 volts, because that's still all the voltage around, divided by this higher 25 ohms, higher than when we ignored the resistance of the battery. And what we get now is 60 milliamps. Notice this is a smaller value than when we ignored it of 75 milliamps. So had we completely ignored the resistance of the battery and estimated and then measured, well, we'd find that our estimate was an overestimate. Okay? Reality in this case was that there was more resistance we didn't account for, therefore a lower current. See the way that current and resistance work? Okay? And the voltage difference across the light bulb would also not be the full 1.5 volts like it was before, because it was the only place where the voltage could drop. Okay? Now it's just some portion of it. In fact, it's 1.2. All right? And what's interesting is when you look at that 1.2 is exactly 4/5, because it makes up 4/5 of the overall resistance. And 4/5, I mean 4/5 of the overall voltage of the battery. So 1.2 is 4/5 of 1.5, just like 20 is 4/5 of 25. Okay? So it's the same proportionality. But you don't have to think of it that way, because you can always just plug it back into Ohm's law, which see we're using twice now, to find the voltage drop across, well, the bulb. What if we wanted to find the voltage drop across the battery? Well, we know what the internal resistance of the battery is. We know what the shared current of the whole circuit is. So we could just take 60 times 5, right? 60 milliamps, or 0.06 amps, multiplied by 5 for the battery. What would that give us? I bet you know, 0.3. Okay, you can actually calculate it to make sure I'm not blowing hot air, but no, it's definitely 0.3. How do I know it's 0.3? Because it has to make up the deficit, right? The battery is supplying 1.5. 1.2 is being exchanged or transformed across the light bulb, turned into heat energy. Okay, that leaves another 0.3 to get changed into other forms of energy. Again, heat, batteries heat up, right? From the internal resistance of the battery. See? Because the overall voltage changes have to sum to 0. It's actually called the loop rule. All right? So if we disconnect the bulb and measure the voltage across the battery terminals, we will get the 1.5 volts again. We get the full voltage, because that gets now the only resistance is the internal resistance. As the battery gets older, however, its internal resistance gets much larger. The total resistance of the circuit increases and reduces the current flowing. That's going to cause things to be less bright. So that's that characteristic behavior of devices that run on batteries as the battery gets near the end of its functional period, right? Things don't work right because everything's running on less current than it was designed for, okay? So the bulb gets dimmer, right? And things like that, more complicated circuits or things that make sound, right, start behaving very strangely. So in a dead battery, the internal resistance has become so large that the battery can no longer produce a measurable current, right? Still might be some current, but not enough to run anything. A good voltmeter does not draw much current, all right? What's a voltmeter? It's a way to measure voltage. Perhaps you've seen one. They usually have little prongs, okay? It can, so that way it can measure approximately the voltage across something without influencing it, right? Without actually changing the internal resistance. Well, that's where we leave off. And in the second video, I will continue this discussion of circuits, talking a lot about Ohm's law, energy, and current, voltage, and resistance, but for two types of circuits called parallel and series. So stay tuned for that, or check back when that video is posted. I hope this introductory video on electrodynamics has been both interesting and informative. Thank you so much for watching.